Okay, so good morning, all of you. So, in the previous class, we have seen that forward biasing of your PN junction diode and then reverse biasing of the PN junction diode. So, what is mean by biasing? When we apply external DC supply to the any electronic device, then that we will call it as biasing. Okay, and when we apply DC voltage supply to PN junction diode, okay, now, depending upon the polarity, we calling this as forward biasing or reverse biasing. In terms of PN junction diode, we have a P and N type of you can say material which are chemically combined with the help of fabrication techniques to form a PN junction. Okay, and it is commonly used as or commonly the term used for PN junction is diode. Okay, so, in the forward biasing, when your P type of semiconductor or P terminal is connected to the positive terminal of the battery and your N region is connected to the negative terminal of the battery, then we are calling this as a forward biasing. Whereas in the reverse biasing, your P type of semiconductor, likewise in this particular diagram, you can see that your P type, okay, this is your P type material which is connected to the negative terminal of the battery, okay, and N type material is connected to the positive terminal of the battery. Okay, so this is what the reverse biasing. In forward biasing, we have seen that forward current is there. Okay, and in the reverse biasing, we have seen that there is a reverse current. Okay, so in the forward biasing, you can see that there is narrowing of depletion region. This is what the depletion region is there, and this is narrow because of, you can say, forward biasing, or you can say this positive terminal of the battery, which will repel all the you can say holes in the P region, okay, and start crossing this junction and they pass to this, you can say they cross this junction, okay, and then they try to move towards this positive direction, whereas the electrons in the N region, because of this negative polarity, they repel from this negative polarity and they try to cross this junction N to P and then start moving around this. This is what the forward you can say flow of electrons, and then this is what the reverse direction is, the your direction of your conventional current. Okay, so what is this current? This current is known as forward current, or you can say the current which is given by these electrons is called as electron current. Whereas if you see this in reverse bias conditioning of PN junction diode, okay, so if now in this reverse bias condition your P side, or you can say P region, is connected to the negative terminal of the battery and your N region is connected to the positive terminal of the battery, what happens? So your that holes in your P region, okay, they attract from this negative terminal, okay, and then your electrons from this N region, they attract towards this positive terminal of the battery, and this, you can say, this makes that widening of the depletion region. When this depletion region widens, okay, so it forms this negative immobiles ions on the P side and positive immobiles ions on the P side, sorry, and on the N side, okay, and this depletion region, you can say, widens, okay, but still as there are some free electrons are there, likewise here the free electrons are there in the P region, okay, which are minority charge carriers, and in the N region we have free holes which are minority charge carrier. They takes place, or they comprises one that current, okay, and that current value is very very small, and that current is called as reverse current. Okay, likewise in the forward biasing we have forward current, in the reverse biasing we have a reverse current, and that current which is basically due to the minority charge carriers, okay, due to the minority charge carriers. This we have already seen, and now in the today's class we will talk about VI characteristics of a diode. Okay, so in the today's class we will see VI, or I will write it in terms of words, that is volt ampere. Okay, volt ampere. So in short forms it is known as VI. Okay, volt ampere characteristics of a diode. Okay, VI characteristics or volt ampere characteristics of the diode. So why this VI characteristics is important, or voltage ampere characteristics is important, in order to understand the response of your diode, okay, when it is connected to the electrical circuit. So we can judge that the response of the diode depends on the volt ampere characteristics, and it is also commonly called as VI characteristics. So if you see that VI characteristics, okay, we have forward bias diode, and we have seen the reverse bias diode. Okay, so the VI characteristics comprises of your forward bias characteristics and reverse bias characteristics. Okay, so so before going to this, okay, so we'll divide this. Okay, so we'll first see forward characteristics of PN junction diode, and then we will see reverse characteristics of PN junction diode, and then we will combine these forward characteristics and reverse characteristics in a single waveform. Okay, so first I will see, you can say, forward characteristics. Forward characteristics. Okay, so your PN junction, now I will connect this PN junction with the forward bias condition. Okay, so I will apply the voltage. Okay, applied voltage across the PN junction diode. So let me draw this circuit first. Okay, so this is what the current. First I will draw, this is current limiter resistor. Okay, and then this is my diode. Okay, so yes, so this is my P side. Okay, and this is my N side. Okay, and this P side, okay, this is positive. I will may mark it as in the this one. Okay, in the uh, symbols. Okay, so this is positive side. So positive side I will connect with the positive supply of the battery, and then this negative side. Okay, this negative side I will connect with the negative supply of the battery. Okay, so this long edge represents the positive of the battery, and this short edge represents the negative edge of the battery. And this is my R. I will write this as my current limiting resistor, and this is what the diode terminal. Okay, so this is what the diode, and the voltage across this diode. Okay, so voltage across this diode is VF, or you can say forward voltage. Okay, and then the current which is flowing through this diode is known as I, or you can say I will write it as in terms of F, so that is forward current IF. Okay, and this is what the direction of the current. Okay, so I will repeat this. So when you applied a voltage, okay, this is my V. When you apply voltage to this diode in this forward bias conditioning, or you can say positive side of the terminal is connected to the P side of the P region of this diode is connected to the positive terminal, and then N region is connected to the negative terminal. So this is forward biasing. So if you apply some voltage in this forward biasing diode, okay, for this circuit. Okay, so then we will have to plot. Okay, so in the forward biasing, what we have seen, that in the forward biasing, whenever there is a forward current which is less than the cut-in voltage. Okay, we talked about cut-in voltage, or you can say barrier potential. We talk about uh, uh, um, uh, uh, barrier potential. Okay, so that cut-in voltage, if it is less than that V, which is less than our if it is in the barrier potential, so your this curves, like you can say that current which is very very less. Okay, and then it start exponentially increasing. Okay, these characteristics we will see in the lab class. Okay, so if I plot this across my voltage, okay, that is my VF, okay, that is forward voltage, and then forward current. I will plot these characteristics in terms of forward current and forward voltage. Okay, and if I start applying this voltage, okay, V, so at particular cut-in voltage, okay, I will specify this value as cut-in voltage, cut-in voltage, or you can say a barrier potential. Okay, and after this barrier potential, it start exponentially increasing. It start uh, just wait for a minute. Okay, okay, so what I was discussing, as long as this there is cut-in voltage. Okay, So this is what the cut-in voltage, or you can say uh, barrier potential. Okay, so if that cut-in voltage, or you can say whatever applied voltage, okay, if it is less than this cutting voltage, your diode won't conduct. Okay, so this current will be very less. Okay, and then it start increasing, or it exponentially increases. Okay, after when it cutting voltage is increases. Okay, so for silicon and for germanium, okay, for silicon, you can say cutting voltage is from zero point 0.6 to zero point 0.7, okay, depending upon the diodes. Okay, and then for germanium, okay, this we have already discussed. Okay, for silicon it is 0.6 to 0.7. Okay, you mostly you will see that it is in this range. And for germanium, okay, it is 0.2 to 0.3. Okay, this is cut voltage. And if your V, that is your applied voltage, if it is less than this particular value, so your I, that is current, is not increasing. Okay, and when it passes that applied voltage, if it increases by this value cut in voltage, it start exponentially. So your current start exponentially increase, that you can see in the VI, or you can say volt ampere characteristic. Okay, so if I want to specify, okay, if I want to specify that if this is my point, or for the cutting voltage, okay, this is 0 and this is P. So from 0 to P, okay, from 0 to P, your current flowing is very less. Whereas if you take this another point, okay, on this curve, the current flowing through this point P to point Q, okay, is exponentially increase. Point P to point Q is exponentially increase. And if we talk about these two particular points, okay, so if you want to calculate a dynamic resistance, okay, that will theory is there. Okay, so uh, this particular region, okay, so this is nothing but change in your VF, delta VF, or you can say change in VF. And if you take this measure this vertically, okay, so this is nothing but your change in your IF. Okay, and that's why we can calculate the dynamic resistance of that particular circuit. Dynamic resistance. So we are not going to that dynamic resistance or these values. Okay, what I wanted to convey is that this is what the forward characteristics of the diode. When your diode, which is when your diode, or uh, uh, when your VF, okay, voltage across that diode, if it is less than the cut-in voltage, the current flowing is very small. Okay, and if it is greater than the cutting voltage, the current flowing is exponentially, you can say, increase. Okay, the next one we can see the reverse characteristics of your PN junction diode. Okay, so next we will see that is the reverse characteristics of PN junction diode. Reverse characteristics of PN junction diode. Now I will draw the circuit. Okay, this is your forward biasing condition. Okay, and the same circuit I will draw, only the polarity, or you can say voltage polarity, I have changed. Okay, so this is the current limiting diode. Sorry, this is current limiting resistor. This is your diode terminal. Okay, and then voltage across this diode is VR, that is reverse voltage. And then I look at the battery terminal. So I will make this as a negative. Okay, so this is my P side, or you can say positive side, and this is negative side. So positive side is connected to the negative terminal of the battery, and your negative side of the diode is connected to the positive terminal of the battery. So this is what in the reverse, you can say, biasing. Okay, and then we can draw a reverse characteristics of PN junction diode. Okay, so the current which is flowing through this, so you can see that direction of the current in this forward bias, the direction of the current is like this. Okay, so it is going from, you can say, positive terminal of the battery to the negative terminal, or from this way. So here the current direction is like this. Okay, so this is your current direction. So what is that current? That is your uh, IR, that is reverse current. Okay, I represents the current and R represents the reverse current. Okay, so here you can consider that reverse voltage across the diode, that is your VR, and while current flowing through the reverse current is your IR, which is flowing due to the minority charge carriers. Okay, then we can draw a current, or you can say IR versus the VR curve. Okay, so this is, yes. So this is, you can see that this is in the first quadrant, okay, because all the values your V and I, okay, here in the forward characteristics, okay, your voltage and your current values are, you can see all both are positive, so it comes in the first quadrant. Whereas if you see here, okay, so I'm drawing it this curve, that is in terms of IR, and then this is my VR, okay. So this curves goes like this at some steady point, and then it will exponential. So this is what the, you can say, the breakdown of the diode. Okay, reverse voltage. Okay, when we applied reverse voltage to this particular diode, okay, so this is defined as, you can say, this we have given reverse polarity, or you can say reverse voltage is applied as long as there is, you can say, that breakdown voltage is there. So this VR is there, so you can see that this is towards minus VR, and this is your minus IR values. Okay, as long as you your polarity, reverse polarity of this voltage is increases, okay, at certain point your diode breaks. Okay, so at certain point you will get a you can say straight line curve, and then it exponentially goes down. Okay, and that particular value is called as breakdown voltage of that diode. Breakdown voltage of that diode. So this is your reverse current, IR, and then this is your reverse voltage, reverse current and reverse voltage. So as we increase the reverse voltage, your reverse current is also increases initially. Okay, likewise in this curve you can see that your reverse current is also increases, okay, initially, but after certain voltage the current remains constant. Here you can see that after certain voltage, okay, here it is increasing somewhat, and then after certain voltage it is constant, which is equals to your reverse saturation current. Okay, which is equals to your reverse saturation current. Reverse saturation current. Okay, and it is defined as in terms of I zero. Okay, I zero. So though then your reverse voltage is also increased. So that point is there. Okay, this point, if I represent this point as the point A, so the point A, where that breakdown occurs at your reverse current, which increases rapidly in this curve. Okay, here your reverse current is increases rapidly, and that point is called as breakdown voltage, or you can say reverse breakdown voltage. Reverse breakdown voltage, this is what the knee, or you can say in some language you can consider this as a knee. Okay, so now we have seen that forward characteristics of p-n junction diode, reverse characteristics of p-n junction diode. Now I will draw a combine, or you can say a complete VI characteristic of diode. So in order to understand VI characteristics of diode, I have divided it in terms of forward and reverse. But whenever there is a question that draw a VI characteristics of diode, you have to draw it completely. Okay, so complete VI characteristics. So I will draw it again. Complete VI characteristics. So this is my current. Okay, This is my current, which is in terms of, okay, in terms of milliampere. I will write this type of this current is, I will make it as a forward current, okay, and this side I will make it as a reverse current IR, and which is in terms of microampere, okay, and this is my forward voltage. I will draw it is in VF, and this is my reverse voltage, that is VR. Now I will make this as small change, and then it goes to exponential increase, okay, and this is my cut-in voltage. Then it increases slightly, and then it will give the steady state value, and then it rapidly increases, okay. So this is what my I0, or you can say reverse saturation current. This is what the breakdown region, this total region is called as breakdown region, because here your diode breakdowns after, you can say, certain breakdown voltage, okay. And yes, that is what the complete diagram, okay. So here, this is what your VI characteristics. So in the forward characteristics, it is, you can see that there is initial forward current, okay, initial forward current is small, this one, okay, as long as there is a bias voltage, or you can say a cutting voltage, okay, that is less than your barrier potential. And at certain voltage, when it closes the barrier potential, your current start increasing rapidly or exponentially, okay. The voltage at which your diode current start increasing rapidly is called as cut-in voltage, okay. And the voltage at which your diode is, you can say, breakdown occurs, okay. Here you can see that there is diode, when we increases that reverse voltage, at particular point your diode breaks, okay. So that is called as breakdown voltage, or a reverse breakdown voltage, reverse breakdown voltage. Your reverse current before your breakdown is very very small, okay, and this reverse current is practically, you can say, negligible, practically negligible. Yes, so I think we will stop it right now.